ShapeMetrix mapping with special focus on underground. The practice for mapping has several disadvantages. We need access to the rock in order to get orientation measurements, could be hazardous. And the implications are that data are incomplete, are biased, and sometimes hard to reproduce. A solution to that is an entity called 3D images, which can be used for mapping. So what's a 3D image? A 3D image is the combination of topographic information, which means X, Y, Z coordinates from points of the surface that are connected to each other to a surface mesh, and a real digital photograph that's draped over the 3D image. The photograph and the mesh are always perfectly aligned, since all the measurements directly originate from the photographs. So this is a straightforward source when assessment of rock mass shall be performed. So how to generate such a three-dimensional images? Two photographs can be taken freehand using a calibrated camera from two slightly different imaging positions, and a software automatically calculates a three-dimensional image out of that. We do not need to survey the camera locations or the distance between the cameras. For more complex areas, overlapping photographs can be used, and the software uses common topographic and image information in order to align the pictures to each other to get a so-called merged 3D image. This can be done, of course, also on the ground. So what's the difference to classical photogrammetry? As mentioned, no surveying of camera stations is required. We can use standard cameras equipped with zoom lens, and there are simplified orientation procedures available. So what can be done in terms of mapping? Standard features are the mapping of joint traces, surfaces, locations, distances and areas, everything done directly on a three-dimensional image itself. A joint surface, for example, can be mapped by visually determining the location of it and just clicking on it, and an automatic region growing algorithm that searches for more or less planar information on the 3D image or within the mesh directly grows up an area and shows the mean orientation of the underlying mesh. This can also be used then to group the measurements into different sets as shown by different colors within this animation. Joint traces or fractures are mapped by outlining the visible trace onto the 3D image, and this is a line in 3D. The software fits a plane to that set of points, which instantly provides dip and dip direction of this joint trace. In addition, the joint trace can be, or the orientations of it can be modeled by elements as shown with these discs. Although it's possible to define different sets by the operator, there's also a function within the software that automatically groups joint orientations into sets, a so-called clustering algorithm. As shown in this animation, unordered set of discontinuities are now grouped into several sets and colored. Some of the derived features are stereo nets or roughness profiles, the determination of the true spacing, or contour plots, which are directly shown within the software. So why are 3D images interesting for rock mass characterization? The system is easy to apply, it's fast, it's rather flexible, the hardware is not expensive, and it delivers a high quality documentation and allows contact-free measurement. It allows more time on site even for assessing other phenomena that are non-geometric, which means the geologist has more time to assess things like joint filling, rock quality or water. It's a supplement and not a substitute. The system is now in use in over 25 countries worldwide, not only underground but also on surface. This is a quick overview on the ShapeMetrix